Hi, welcome to another video on electronics. So in this video we will focus on bipolar junction transistor, which is very popularly known as BJT. In this video we'll see the basics and few applications of BJT. Before we start, so let us know some prerequisites. Of course, you should be knowing Ohm's law, KCL, KVL, and of course some basics of semiconductors and PN junction is expected for better understanding of the content of the video. Of course, okay, with these prerequisites, let us start the now. We are trying to consider a semiconductor. So this is semiconductor. As we know that conductivity is neither of a conductor nor of an insulator. So this can behave like an insulator or a conductor depending on the temperature that what we are operating in. So we know that silicon is the best known semiconductor. Now this is how the covalent bond of the silicon will be looking like. So just to quantify the number of silicon atoms per cubic centimeter. When I say per cubic centimeter, so assume that you have a cube of all sides of the cube as 1 centimeter, 1 centimeter, and 1 centimeter. In this volume, we're going to have the number of silicons as 5 into 10 power 22 atoms. So these many atoms per cubic centimeter will be there in a silicon structure. So in a silicon material, we're going to have these many number of silicon atoms per cubic centimeter. So at a temperature of 300 Kelvin. So of course we know that silicon has got four valence electron, and these assume that okay, this is one electron, one electron, one electron, one electron of this particular silicon atom. This is sharing one electron with this, and this is sharing one electron with this. This is sharing one electron with this. This is sharing one electron with this. Now this becomes a covalent bond. So each silicon atom is sharing one valence electron with the neighboring four silicon atoms. So that now this becomes a covalent bond. This particular covalent bond is intact. All the covalent bond will be intact at, at 0 Kelvin, at 0 Kelvin or at 0 degree centigrade. So now when the temperature is 0, it is intact. So not a single covalent bond is broken. But at 300 Kelvin, so there will be these electrons will be getting enough energy so that they come out of the covalent bond. Assume that if this covalent bond, suppose this electron comes out of the covalent bond, which is E, which will create a vacancy of electron here. You can see this is a vacancy. When there is a vacancy created, we call it as hole. So this is called as hole, which is nothing but vacancy of electron. Suppose if one more electron comes out of that particular covalent bond, so there is a hole created. So now under normal condition, that is when the temperature is elevated, we're going to have n number of electrons leaving the covalent bond, which will create the p number of holes. So this n and p are always equal. So n and p are always equal in this pure semiconductor. This pure semiconductor, I'll call it as intrinsic. So this is intrinsic semiconductor. In intrinsic semiconductor, number of holes is equal to number of uh, electrons, which we call it as Ni. Ni at 300 Kelvin, it will be almost equal to 1 into 10 power 10 electrons per cubic centimeter. We're going to have these many number of free electrons per cubic centimeter. So this number looks very huge. But if you relatively compare with the number of silicon atoms, so suppose if you say this is silicon density divided by the electron density. Electron density, what you have, it is 5 into 10 power 22 by 1 into 10 power 10. So this will become 5 into 10 power 12. So what is the meaning of this? Meaning of this is for every, this is for every 5 into 10 power 22 silicon atoms, I have only one free electron. There is only one free electron, meaning that this is a very less number. So sorry, okay, this is what, this is not 22, this is 12. For every 5 into 10 power 12 silicon atoms, you have only one free electron. So what is the total volume? What is the volume we are considering? We are considering 1 centimeter cube, in which I have these number of silicon atoms and I have these number of free electrons. So if you quantify the number of free electrons relatively, for every 5 into 10 power 12 silicon atoms, you have hardly only one free electron is free. Only one electron is free. That is, it is free to move around, which is a very less number. So this is not able to conduct the current. So what we do, we try to increase the number of electrons. So one way to increase electrons is you increase the temperature, number of electrons will increase. But it is not recommended to increase the temperature of the substrate so that number of electrons will increase. We do the process called as adding the impurity, which is called as doping. So doping is nothing but adding the impurity to a pure semiconductor, to an intrinsic semiconductor. If you dope the impurity, then we have extrinsic semiconductor. So that's what is this. Here I'm having it phosphorus. Phosphorus is the impurity which is being added to the silicon. You can see I'm adding, pictorially I'm representing only two phosphorus atoms are added. Now this phosphorus is a pentavalent component, so pentavalent chemical. So it has got 5 valence electrons. So then it is sharing with this and this. One is free now. One is extra. You see, this is sharing with this and this. One is extra. Every added phosphorus will have one extra free electron. Will have one extra free electron. So here we said, in the earlier case we said this is NP is same and it is Ni. So we can write N into P is equal to Ni square. So this equation is valid for whether you consider pure or extrinsic semiconductor. So now what we'll do is, so what is this? We know that we had 5 into 10 power 22 atoms of silicon per cubic centimeter. So I can add the phosphorus or a boron. So if you add a phosphorus, one electron is free. If you add a boron, can you see here? I'm adding a trivalent component. So I can see it has got only 3 valence electrons. It is sharing with this. Okay, okay. Let us just assume that it is sharing with this and this. You can see this is of silicon. So you can see one is vacant. So this boron is sharing with only 3. So this silicon is sharing 1, but this boron doesn't have one electron to share with this. So I have a vacancy. So this is what the hole. Meaning every added trivalent will create a hole in case of this type of semiconductor. So here we have a hole whenever you add a trivalent. Here we have an extra electron when we add a pentavalent. So this is called as N-type semiconductor. This is called as P-type semiconductor. P-type semiconductor. Now these are extrinsic semiconductors. Now let us try to identify how much is the doping that you can do. I can add 10 power 15 to 10 power 18 atoms of either phosphorus or boron per cubic centimeter into the silicon atom. So depending on how much you are adding, whether you are adding 10 power 15 or 10 power 18, If it is 10 power 15 added, I will say this is lightly doped. This is lightly doped. If it is 10 power 18 added, I will say it is heavily doped. It is called as heavily doped semiconductor. If it is like 10 power 16 doped or 17 doped, I say it is moderately doped. Moderately doped. So this is the doping concentration, whether you have 10 power 15 atoms of phosphorus or boron per cubic centimeter added to the to the silicon, if then it will be called as if it is n type, it is called as n minus. If you are adding too many, then it is said as n plus. If you are adding only 10 power 16, then it is said as n. So similarly, I can have P minus, P plus, and P. What is this P minus? P minus is adding boron with a concentration of 10 power 15 boron atom per cubic centimeter. What is this N plus? It is adding phosphorus at the rate at a concentration of 10 power 18 phosphorus atoms per cubic centimeter. So what is this NRP? It is adding boron with this much concentration, adding phosphorus with the amount of concentration which is 10 power 16 atoms of uh, dopant is added to this. Now, we know that when you add phosphorus, one extra electron will come. When you add boron, one vacancy is created. So, what will be the number of electrons that will be there in N type when you add 10 power 18? So, we will define one parameter called as n of n. It is number of electrons in N type is equal to number of donors that you are added, because every phosphorus you are adding will donate one electron. Assume that this is 10 power, assume that this is 10 power 18. If this is 10 power 18, then can I find what is the number of holes in the n-type semiconductor? This is given by, as I said, this n into p is equal to ni square is valid for even the extrinsic also. Meaning, I can say n of n and p of n is equal to ni square. So this we know. This is number of electrons in n-type, number of holes in n-type. So we know what is number of electrons in uh, n-type, which is nothing but how many you are added, which is 10 power 18. 10 power 18 atoms of phosphorus per cubic centimeter, which happens to be the number of electrons. Which happens to be the number of electrons. Now, can I find what is P of n? From this, can I write P of n is equal to ni square by n of n? So can I write it as ni square by n of n? So what is ni square? Ni is this much. Where is that? It is 1 into 10 power 10 square divided by n of n is 10 power 18. So I have 10 power 20 by 10 power 18. So this is actually 10 power 2. What does this actually mean here is, if you are having 10 power 18 phosphorus doped into this, the number of electrons in N type will be 10 power 18 electrons per cubic centimeter, whereas number of holes will be 10 power 2 holes per cubic centimeter. So from this, when we say this is huge compared to this, so that's why this is called as in n-type semiconductor. In n-type semiconductor, electrons are majority carriers, because you see the number 10 power 18, whereas holes are minority carriers. Why it is minority? Because their number is very very less. This is how you can quantify the majority and minority carriers. In the same lines, for p type, we have uh, ni square is equal to p of p and n of p. What is this p of p? It is number of holes in p type, number of electrons in p type is ni square, which is nothing but 1 into 10 power 10 whole square. So assume that I am adding boron, which is 10 power 16 atoms per cubic centimeter. So now this is called as number of acceptors. Because when you add single boron, it is ready to accept one extra electron because there is a hole. So that is equal to P of P. So then what is N of P? Number of electrons in P type is from this equation Ni square divided by P of P. So what is Ni square? It is 1 into 10 power 20. This is 10 power 16. How much I have? 10 power 4. What is this? This is N of P, electrons per cubic centimeter. So P of P is 10 power 16 holes per cubic centimeter. N of P is 10 power 4 electrons per cubic centimeter. Can you see now? For p-type semiconductor, we have holes more than the electrons, so that's why holes are called as majority carriers. These are called as minority carriers because they are less in number. Okay, with this understanding of the uh, p-type and n-type, let us move on to p-n junction. Try to find out what happens if it is reverse bias and power bias. We know that when you connect, let me just show this to you. Now assume that this is the situation when p-n junction is reverse bias. Can you see we are having minus connected to p and plus is connected to n. So this is a situation of a reverse bias condition. Under this reverse bias condition, if you have an electron emitting to this, let us see what happens to that. So now why we are interested in seeing this type of p-n junction and inject an electron. So before we actually try to understand this, so let us focus on what is a BJT. So we know that a BJT, it is nothing but bipolar junction transistor. We will going to have the structure like this. So this will going to have a very thin layer of, this is base, and you're going to have collector, and this is emitter. So this is, so now this can be of N, P, N, or it can be P, N. This can be N, P, N, or it can be P, N, P. Meaning we can have two configurations of a transistor. This will be N, P, N transistor, or it can be, see now this is P, N, P transistor. This is N-type. Now this is base. Arrow mark always indicates emitter. The identification of the terminals from the symbol, and this is collector. Again, this is base. This indicates this is emitter, and this is collector. So now this is the symbol of a BJT looks like this or this. So this is NPN transistor. This is PNP transistor. So you can see here there is one PN junction. There is another PN junction. So there are two junctions here. Now let us assume that this is forward bias. So what do you mean by forward bias? You have a positive voltage here and you have a negative voltage here. If this is the condition. Now you know that. So when you have this positive, this is P is getting positive, N is getting negative. So this is like forward bias. So you have a junction which is base and emitter. I can say there is a emitter base junction, and there is another, this is a p junction, this is a p junction, there is another p junction which is collector collector base junction. Assume that I'm connecting 0.7 volt or 0.8 volt. If I connect 0.8 volts, so this is now forward biased because this is getting positive, this is getting negative. So let me assume that I'm connecting some 1 volt here. If you're connecting 1 volt, when you're connecting 1 volt here, if you basically see at this point you have 1 volt, at this point you have 0.8 volts. See now, this is P, this is N. So N is having more voltage than P. So P is hardly having zero point 0.8, whereas N is having 1 volt. So E is the voltage at N is greater than voltage at P for this particular case. So in this case, voltage at N is 0, voltage at P is, so here Vp is greater than Vn. So that's why this is forward biased. Whereas here between these two, because of this 1 volt, I'm getting this as 1. Because of this 0.8, I'm getting it as 0.8. So what is the voltage at here? 0.8. What is the voltage at here? 1 volt. So this is P, this is N. So Vn is greater than Vp. So you have this collector base junction. This junction is reverse bias. This is reverse bias. So now you have emitter base junction forward biased and collector base junction. This is emitter base junction forward bias. Collector base junction is reverse bias because you applied zero point 0.8 and 1 volt. So now suppose if I apply zero point 0.2 volt here. Now in this case, when it is zero point 0.2 and this is zero point 0.8, here you having zero point 0.2 volt, here you having zero point 0.8 volts, then this will be forward biased. So if this is zero point 0.2, then this is forward biased, that is collector base junction. Emitter base junction is also forward biased. So now let us see, when this is forward biased, what happens? When this is reverse biased, what happens? That is, when does this collector base junction is reverse biased? When you have 1 volt here, when you have 1 volt here, it is reverse biased. So in a PN junction which is reverse biased, if you get an electron in that junction, what happens is, this is what is the observation. So this is what we are trying to say here. See, just a minute. This is what we are trying to say. In a PN junction, if it is reverse biased, if an electron is get injected by some means, what happens? Now since electron is injected here, now we can see there is a positive potential. These electrons will be drifted towards this uh, positive terminal which is there at the inside. So these electrons will be attracted by the positive voltage which is there at this point. So these electrons which are injected will be coming and reaching this particular terminal. So we will see whether similar type of situation does it exist in a BJT. In a BJT. For that, let us try to understand this picture. So let us try to understand what happens here. See now I have a condition. So let me just show you. Let me cover some of the points and then try to make you understand what happens if you have a condition which is like this. So now see what you are having. See VBE is zero point 0.8 volt. So now this is forward biased, and of course this PN junction is forward biased. And one very interestingly, one more thing I forgot to say is, so here in this case of BJT, this base, this base is thin in dimension. So it is very thin and it is also lightly doped. It's a lightly doped. So it's basically like P minus. It is lightly doped. Thin is the base structure, whereas the emitter is actually heavily doped. So even though it is NPN, it's actually N plus P minus and N. What is this N plus? N plus is heavily doped emitter, because the name of the this is called as emitter because it emits carriers. So in case of NPN transistor, it emits electron. This is called as collector because it collects the carriers. So it is collecting the electrons. This is called as base because it can control the number of electrons which are reaching this collector. So now, coming to concentration of doping, emitter is heavily doped, uh, base is lightly doped, and the collector is moderately doped. So that's what we discussed in the previous slide. So when it is 10 power 18, we call it as heavily doped. When it is 10 power 14 or 15, we say it is lightly doped. If it is 10 power 16, we say it is moderately doped. So now we have a situation where this is forward biased, and since this is lightly doped and you have not too much number of holes, so that's why you can see there is small amount of holes are repelled by this. Since it is heavily doped, there is a huge amount of electrons entering this p junction. So now, can you see this electron is entering this p? Is it is it similar to this situation? Can you see here? So did you had that situation here where an electron is coming to this p side? So this is exclusively a p junction. Now, do we have similar type of condition over here? So there is an electron being injected into this p region, What happens to this? Since this area is very less and number of holes are also less, what happens is this, can you see, this is penetrating into this. Since you have positive voltage, these electrons will be crossing this depletion region. These electrons, because there is an attraction here and you have huge number of electrons coming here, these electrons will be moving towards this terminal, which is the collector terminal, because they are having huge attraction and this recombination is also very less and this area is also very thin. So the electrons are trying to cross the depletion region. That's what happened here. Can you see? Even though this is reverse bias, the electrons which are coming from the emitter will cross this depletion region even though this is reverse bias. Can you see now this is certainly reverse bias. In spite of this is being reverse biased by this voltage, the electrons are collected by this positive charge. That's how the emitter or the electrons which are emitted by the emitter are passing through base with very less recombination and reaching the collector here. The same thing is depicted here. You can just have a look at this. What is the amount of recombination you can think of? I'll show you. So what you have is, see here, this is how this is the electron. We know that the current is in the direction opposite of the electron movement. Electrons are actually moving here, that's why the current is going down. And you can see this is the direction of current is same as in the direction of the hole, so that's why this is your base current. And you can see the electrons are going to collector, and this is how the electrons are moving, but the direction of current is in exactly the opposite direction. Here there is some amount of holes and electron get recombined in this base structure. Since this base structure is very thin and lightly doped, we don't have much of the electrons are not recombined because you have very less number of holes and very less number of electrons will get recombined here. So we have current IE is equal to some amount of recombination happens, which is IB plus the remaining current, which is the collector. So that's why IC is given by IE minus IB. IE minus IB. So when emitter base junction is forward biased, even though collector base junction is reverse biased, we will get the current flowing from, or the emitter electrons will move from emitter to causing a current of IC here, so that current flows to that. For that, I have to first have the forward biasing of this. So VBE is a must. VBE is a must. So I have to have this as positive voltage, and this is positive such that this is reverse bias. Such that this is reverse bias. Suppose if you reduce this forward bias, this positive voltage, assume that this was plus 1 volt. If you make it to 0.6, 0.4, zero point 0.2, what happens? Then the attraction to the electrons will reduce. Then this current will reduce. Then this current will reduce. So that we'll see in the IV characteristics of BJT. So what we have observed here is uh, emitter base junction is forward biased and collector base junction is reverse biased. So now, so we have three different regions of operation of the BJT. So you have emitter base junction and collector base junction. If the bias of this is forward bias and if this is reverse bias, then we say this as this is reverse bias, that is this is called as active region. Active region. Again, same emitter base junction is forward biased and collector base junction is also forward biased. So then we say this as saturation region. Saturation region. Suppose if emitter base junction is reverse biased, whether you forward bias this or reverse bias this, irrespective of this, there will be no current, because when you reverse bias it, there is no current flowing from this base to emitter at all. So there are no holes, there are no electrons. So then it is called as cutoff region. So these are the three regions of operation of a BJT: active, saturation, and cutoff. So these regions will be encapsulated or can be observed in a characteristics called as IV characteristics of, this is IV characteristics of BJT. In this IV characteristics, we will plot VCE as x-axis and IC as y-axis parameter. Now, if you start increasing this VCE initially from zero, this actually goes like this, and then it becomes constant. If you, this is for a particular value of IB. If a particular value of IB is flowing, this is how it looks. If you increase the value of IB, this actually goes like this, and then again you can see this current increases. So this is for a different value of IB. If you further increase the value of IB, it just goes like this. This is IB3. So here we say this is this entire region. This entire region is called as active region. Active region. And you have this region where this is VCE. This may be around 0.2 volts. If VCE is less than 0.2 volt, we will be operating here. This is called as saturation region. Saturation region. And you may have one more thing here which is almost as zero. This is called as cutoff region. So in this cutoff region, IC is zero because there is no collector current. So in active region, the collector current is almost constant. Can you see it's almost constant here? Whereas in saturation region, current reduces as you reduce your VCE value. So these are the three regions of operation of the BJT. One is called as active, saturation, and cutoff. So in this, IC is constant. Here IC is varying. Here IC is actually zero. So there is no current. Current is constant here in active region. In saturation region, it is varying. It is varying. Here, the voltage, this is VCE can be any value. Here, VCE has to be less than 0.2 volt or so. So here, VCE should be greater than 0.2 volt. So these are the typical ranges of voltage. Now, we saw that so there is a IB current flowing through the base and there is a IC that will flow through the collector. This IC is very large compared to IB value. This, if this say this is IB and if this is IC, this IC is beta times IB. So this is called as beta, which is nothing but current amplification factor. So if I write what is beta, this beta is nothing but current amplification factor. So this beta is always far greater than 1. Its value ranges from 50 to maybe 300. 50 to 300. So IC is equal to beta times IB. Beta times IB. If IB is equal to 10 microampere, assume that if beta is equal to 100, then what is IC? Then IC is equal to 100 into 10 microampere, which is 1000 microampere, which is 1 milliampere. Can you see? If there is a current of 10 microampere flows here, then there is a current of 1 milliampere flow here, provided the beta of this is 100. Beta of this is 100. So now this is the property of the BJT. You forward bias emitter base junction, reverse bias the collector base junction. See what happened to the IV characteristics. So let us try to uh, get this graph using a simulation. See now what I'm having is, let me show you what I'll do using simulator. So since this BJT is called a current control device. So this BJT is called as current controlled device. Current controlled device. Why it is called as current control device? Whatever IC that you are having in your collector is proportional to IB. That is the base current. Since the collector current is controlled with the base current, it is called as current controlled device. So let us try to get the IV characteristics from the simulation. So this is, now let me have some limiting resistor here. Let me apply some voltage here. Let me call it as some Vx or some V1 or VBB. Let us have a resistor here which is, let me say it as RC. This is RB. This is base, collector, emitter. Let me ground it here. Let me have a more voltage source which is VCC. So now let us try to understand some relations. So we have a relation of IC is equal to beta times IB. So there is one more relation that uh, IC is also equal to something like IS e power VBE by VT, where VB is this voltage. This is VB. So whereas VT is nothing but thermal voltage. Thermal voltage, which is nothing but KT by Q. This is VT. So where K is the Boltzmann constant, T is the temperature, and Q is the charge of an electron, which will be at room temperature 26 millivolts. So this IS is reverse saturation current which will be in the order of 1 into 10 power minus 13 to 1 into 10 power minus 15 amperes. This is the range of IS. So now let us have a simulation. So let us try to get an IC of 1 milliampere. So let us assume a resistance of 100 ohm here. Let us assume a resistance of 10 kilo ohm here, and let us apply 1 volt here. And let us try to see what should be VB applied so that 1 milliampere flows here. I want to have a current of 1 milliampere flowing to the collector, for which I have to apply sufficient base current. So with this IC is equal to 1 milliampere. So let us assume that IS is equal to 1 into 10 power minus 13 amperes. Let us assume VT is equal to 26 millivolt. So from this equation, I can find what is VBE. VBE can be written as, I can rewrite that as VT multiplied by ln of IC by IS. That is slight rearranging the equation. I can write this. So substituting this VT as 26 millivolt and natural log of 1 milli by, that is 1 into 10 power minus 3 to 1 into 10 power minus 13. This comes out to be 596.8 millivolt. If I'm not wrong, let me just do that. It is 26 exponential minus 3 multiplied by ln of 1 exponential minus 3 divided by 1 exponential minus 13 close. Okay, 598.6. This is 598.6 millivolt is the voltage that should be available here. So now we also know that IB is equal to IC by beta. So then this is 1 milli by 100 is actually 10 micro. Suppose if 10 microampere flows here with a VB of this much, then how much will be the drop? The drop is actually 10 exponential of minus 6 into 10 exponential of 3. Can you see you have a drop of 0.1 volt here. Here you want to have 0.598.6 plus 1 plus 0.1 volt here. VBB is actually equal to IB into RB plus VB from your KVL expression. So KVL expression, the voltage applied is this drop plus this drop. So this drop we know, this drop also we know. So then what should be this VB? This VB should be 0.698, okay, 6986 volts. If I apply 698.6 millivolts, then I should be getting 1 milliampere here, 10 microampere. And let us try to see what is this voltage drop. If this voltage drop is more than 0.7, more than 0.2, then this BJT will be operating in active region. So let us go here. You see I'm having the same voltage, 698.6 millivolts. I'm having it as 10k here. This is 100 ohm. See the beta factor, whatever we assumed, we are writing it in a dot model file. So this is dot. This is the representation of this MOSFET having a beta factor of 100 and having a reverse saturation current of 1 into 10 to minus 13 amperes. See, if I apply this much voltage, if it is 1 ohm, if it is 1 volt and this is 100 ohm, if I do simulation, then this IC should be 1 milliampere provided this voltage drop is more than 0.2. So let me run the simulation. Now we can carefully observe how much is the can you see this is IC of Q1, this is Q1 transistor. Can you see it is 0.00102, it's actually 1.02 milliampere. Can you see this IB, it is 10.24 microampere. We were expecting actually 10 microampere. You have a slight error of 0.24 microampere, which is acceptable. Can you see what is voltage at collector? It is 0.89, which is far more than zero point 0.2 volts. So the BJT is operating in active region. So if you can find the ratio of this and this, that is IC by IB, it will be 100. It will be 100. So what we are trying to understand here is that we did a simulation with the beta factor of this BJT as 100 and its reverse saturation current as 1 into 10 to minus 13. Now I'm trying to have a voltage at this point so that VBE is 0.598.6 millivolts, so that it results in a current of 1 milliampere. So what I can do is I can do a simulation where I can able to vary the voltage like this. So what I'll do now is the same circuit, I will vary this voltage from 0 to 1 volt, from 0 to 1 volt. So now I'm actually varying the voltage from 0 to 1 volt, which is nothing but VCE. I will see how does your IC changes. So what will happen to your IC? For lesser values of VCE, this will be forward biased. So emitter base junctions forward bias means you want to have less current and it increases, it saturates, and then it becomes constant. We are supposed to get this type of graph, this type of graph. So let us see, can we able to see that. So for that, let me do this analysis setup. So I will be changing this voltage V2. I'll be changing the voltage V2 from, okay, let the sweep be of a linear type. Let me start from 0 up to 1 volts in steps of 10 millivolt. For every 10 millivolt NPC, what happens to this? So this is the DC sweep. So earlier we did just the operating condition. Now where we saw the voltage and currents, now we are doing a DC sweep. Now this is not 1 volt, this is varying from 0 to 1 volt with an increment of 10 millivolt. If I run this, okay, just take out of this. I just take out. Okay, let me take out this also for the time being. Now let me save this and run it again. See now, can you see the current is increasing? Current is increasing linearly. Can you see the current is becoming constant, which is almost equal to 1.02 milliamperes, which is constant here. Now this region is active region, whereas a region, can you see this voltage is around 0.238, almost zero point 0.2 volt. So anything less than 0.2 volt, can you see now the voltage has reduced to 186 millivolt. Can you see the current also reduced from 1 milliampere to 965 microampere. Can you see the current is reducing? So here this is saturation region, this is active region, this is active region. If you can see the base current, can you see the base current is hardly 10.24 microampere. We are having the base current flowing here. So this is the region corresponding to active region, this is saturation region. And if you make this voltage as less so that there is no base current means, then there will be no source. How do I reverse bias this? I can make this voltage as 0. If I make it 0 and if I run, you see current is in picoamperes. So since it is picoamperes, it is 0.4 point. This is negligible. So if I change the scale from in picoamperes, let me see it in terms of 1 milliampere. If you see in terms of 1 milliamperes, current is actually 0. You're not seeing any current at all. So that's what is this in cutoff region if it is reverse biased. So let us not reverse bias this. It is 0.6986. So with this, if you run, you can see you're getting this is your IV characteristics. What is this? This is what we saw here. This is what we saw. It was increasing like this and it becomes constant. Now this is for a given value of IP1. So this is 698.6. can change this also. Suppose if I make it one as 700, so maybe 700, 710, and 680. Can you see we have different voltages? So I can do that also. What do I can do is I can go back here and do one more sweeping. So what is that one more sweeping? I'll do the second sweep. So it is now V1 I'm sweeping. So let this be from 0 0.6 to 0.7 in steps of, or maybe 0.7 to 0.7 to 0.9, or maybe 8 in steps of 0.0. So I'm going to get five different plots, different IBs. Can you see you have five different plots? So this is for point 7, this is for point 72, this is for point 74 as my VB value. So as VB, as this V1 changes, the IB changes. You can also see what is the IB. So what I can do is I can just put it in a different pane. What I'll do is I will add a pane for this. So I can add a pane about this. I will place the IB here. Can you see IBs keep changing? So this is IB value. So IB value initially it is 10, then it goes to as you can see here. Can you see it has gone to, you can see here, this is 10, 13, 15, 17, 18. Can you see these are the different currents you are having? So this is your IB. When IB changes, when IB increases, by increasing this, your IC will increase. That's why this is keep going like this. So this is how we can able to. So this is the IB characteristics of BJT. This is also called as output characteristics. Why it is called as output characteristics? The name of this characteristics is called as output characteristics because we are referring to output current and output voltage. So this is output voltage and this is output current, whereas this is input current and input voltage. So if you are referring to input current and input voltage, it is said as input characteristics. So we have two different characteristics: input characteristics, output characteristics, and we have one more called as transfer characteristics. So here you have current and voltage. So in this current and voltage, the input characteristics you are referring to input current and input voltage. In this output characteristics, you are referring to output current and output voltage. In this transfer characteristics, you are referring to the output. This is output current, but the input voltage. Can you see the voltage is input, current is output? So this is what is called as transfer. If both the parameters are of the output, then it is output characteristics. If both are of input, then it is input characteristics. Here this is output, this is input. So that's why it is called as transfer characteristics. So this is transfer characteristics. In input characteristics, you have this is IB, VB. You'll get this way. You'll get this way. In this output characteristics, this is IC and VC. You'll get this way. This is transfer characteristics. You have IC and VB. This is similar to this. So these two are similar. Only thing is that this is beta times of IB is nothing but IC. So these two are 100% same in terms of shape, and this will be having magnitude beta times of this. So this is VB. So this is called as transfer characteristic. So here you want to have some VC constant, here you want to have some IB constant, Here also we want to have some VC. So input characteristics, output characteristics, and transfer characteristics. So this is about the BJT characteristics and its working. In the next video, we'll see BJT as how it can be operated, how it can be used as a switch, and how it can be used as an amplifier. Thank you.